Our bodies are built for rhythm, naturally aligning our sleep, energy, and hormones with the cycles of day and night. Yet, modern life has thrown us out of sync. Late night work, irregular schedules, and the constant glow of our screens keep us awake long past when our brains are programmed to rest. So, what happens when our internal clocks no longer match the world around us, and how does this impact our daily lives and brain function? To understand these effects, we must first explore our circadian clocks. Our circadian clocks are endogenous mechanisms that govern the rhythmicity of our activity cycle over a 24-hour period. The term circadian comes from the Latin word circa and dies, meaning about and day. These clocks modulate essential functions such as sleep, hormones, and body temperature. These endogenous clocks are regulated or entrained by external cues known as zeitgebers, naturally occurring rhythms that help us synchronize our internal clocks with the environment. The sun is our most potent zeitgeber, but we are also influenced by other factors like food and temperature. Returning to the issue of misalignment, many aspects of our lives are affected by our quality, duration, and regularity of sleep. General disruptions to our circadian rhythms, whether due to a bad night of sleep or late night partying, are associated with reduced executive functions such as attention, focus, processing time, and memory. And frequent significant disruptions like shift work or jet lag can have lasting effects on our mental health and brain function. The American Chemical Society has highlighted that the hippocampus, a brain region highly implicated in learning and memory, is particularly vulnerable to the effects of disrupted sleep. But how much disruption do we need before we observe significant changes in our behavior and our brain? To address this, we turn our attention to the hippocampus, which plays a crucial role in spatial navigation. Utilizing a spatial task allows us to examine the behavioral effects of disrupted sleep. Additionally, the hippocampus is one of the few areas of the brain capable of neurogenesis, the production of new neurons, enabling us to investigate the cellular impacts of disrupted sleep as well. So this leads us to our current research question: how does moderate disrupted circadian rhythm affect spatial navigation abilities in a mouse model? So hello, my name is Allison Yang, and I'm supervised by Dr. Mike Antle as we investigate the spatial cognition of mice in disrupted sleep cycles. We have two prongs towards our approach. First, we are examining the relationship between circadian disruption and spatial navigation using the Morris-Water maze, which is a behavioral task measuring spatial memory. Secondly, we are using a cell tracer to measure the survival of new neurons in the hippocampus, allowing us to measure biological responses to disrupted sleep. Hypothetically, if our mild sleep disruption negatively impacts our mice, we should observe poor performance on the Morris-Water maze task alongside a lower rate of neuronal survival in our disrupted groups. So let's get into our experimental designs. We raised our mice in two distinct light-dark cycles. Our control group was kept on a standard 24-hour cycle, and our disrupted group was raised on a slightly shorter 22.75-hour light-dark cycle, which is similar to flying to Vancouver every day. The first aim of our study was to measure the behavior of mice in the disrupted sleep cycles. So we used the Morris-Water maze, which is a pool of roughly 150 centimeters in diameter with a small platform in the northeast quadrant that mice are tasked to find. Our mice underwent 5 training days, completing 4 trials each day, during which they were placed in different quadrants in a random order. The goal is for mice to locate the concealed platform to learn its position. Following this, the mice participated in a probe trial where the platform was removed and they swam freely for 60 seconds. Interestingly, we observed no significant differences in average latency between the two groups. We would have expected our disrupted groups to learn the task slower, but both groups demonstrated similar learning effects, decreasing their time to find the platform over the 5 training days. Likewise, if our disruption was significant, we expected disrupted groups to spend less time in the target quadrant, which was not the case here, with both groups spending similar times in each quadrant. We did, however, notice a significant difference in heading angle, which is the direction the mice take upon entering the pool. The disrupted mice had an average heading angle closer to 0 than our control group, indicating that they were directing themselves towards the platform more effectively. In these heat maps, we see that disrupted groups spent more time in zone A and B of the pool as training days went on, and less time in zone C of the pool by day 5 compared to our control mice. Spending increased time in the center and less around the outside is indicative of an improved search strategy and lower stress in the task. Moving on to aim 2, our goal is to investigate the cellular effects of disrupted sleep on spatial navigation using BRDU, a cell tracer that integrates into the S phase of the cell cycle of new neurons. We injected BRDU intraperitoneally into 1-month-old mice and harvested their brains 6 weeks post-injection to measure survival of labeled neurons. We performed 2 stains, one being DAB, which labels our surviving neurons with a dark brown sediment, and the second is a fluorescent stain, which labels all surviving neurons labeled by our cell tracer and all neurons in our brain. This is still currently in progress, so we do not have results at the moment, but our preliminary results from the behavioral task do not indicate a large effect. However, it is essential to note that we employed a subtle manipulation. Previous studies have used more significant manipulations, such as 8-hour circadian shifts, more akin to rotating shift work or extensive travel across time zones. Our study represents a scenario more similar to advanced or delayed sleep-wake syndrome, a known circadian disorder where individuals will either experience an advancement or delay of their circadian cycles and struggle to align their schedules with a 24-hour world. Our current results from our behavioral task demonstrate that mild circadian misalignment did not significantly impact spatial navigation in our mouse model, which, while a little bit disappointing as a researcher, is a reassuring find. And that brings us to the end of my presentation, so thank you and have a great day.